All right, so today we are looking at sugars. We're looking at Fischer and Haworth projections. We're going to review some basics of sugars. And I just want to take a second to point out that we're looking at this at the elementary organic and biochem level. So if you're watching this video online as an Organic 1 student, just note that the things like stereochemistry that you talk about in Organic 1, we're not going to deal with at elementary organic level. Okay, so just keep that in mind. All right, so I think everybody's pretty familiar with what a carbohydrate is, where you find one, right? They're a major source of energy. They're also known as saccharides or sugars. So a lot of times from here on out, you'll just hear me refer to them as sugars. And there are three types of carbohydrates, mono, di, and poly. So here's a, kind of a picture, cartoon representation of that, right? A monosaccharide would just be one sugar molecule. A disaccharide would be two together, and then a polysaccharide would be group. So today we're only looking at monosaccharides. We'll deal with disaccharides and polysaccharides next week. All right, so monosaccharides, the ones that we're going to be focusing on, are 4 to 6 carbon chains long. They contain either an aldehyde or a ketone, and they're going to have lots of OH groups. All right, so I want to make a distinction here. We're looking at how we classify monosaccharides, not how we name them, okay? Because nomenclature and classification are two different things. So this is just classification, okay? We're not going to deal with nomenclature of monosaccharides in elementary organic and biochem. That's not something we deal with. We're just going to classify them, okay? So the suffix is -ose, and then the base is the number of carbons in your chain. Okay, so if it's a triose, it's got 3. Tetrose, it has 4. Pentose, it has 5. Hexose, it has 6. Right? So the ose suffix, and then the base would just be the number of carbons in your chain. And then there's going to be a prefix of either aldo or keto, depending on if it contains an aldehyde or a ketone. Right? So an aldo triose contains an aldehyde and is 3 carbons long. Aldo pentose, 5 carbons chain with an aldehyde, aldo tetrose, aldo hexose, right? And then here would it be ketones, right? So a ketopentose is 5 carbons long, contains a ketone. Ketohexose would be 6 carbons long, contains a ketone. And again, this is a classification. This is not nomenclature. Not nomenclature. Make sure you understand that this is not nomenclature. When we get into organic chem, we'll deal with how we name sugars, but we're not going to do that in elementary organic. Okay, that's not something that we do in this class. So here's some figures, this directly from your textbook, of different monosaccharides. Right? This would be an aldose. It contains an aldehyde. This would be an aldose. It contains an aldehyde. This would be an aldose. It contains an aldehyde. But this would be a ketose, right? Notice the difference between a ketose and an aldose, right? This would be an aldopentose. 1, 2, 3, 4, 5. This would be a ketohexose. 1, 2, 3, 4, 5, 6, right? And it contains a ketone. Do we see how we classify these? We count the number of carbons in the chain, including the one at the very bottom and the one at the very top. If it contains a ketone, that gives you the keto prefix, right?
Okay.
And yeah.
The names on top, those are the names we're not learning.
Well, there are 3 that you're going to learn. And those are common names. Those aren't IUPAC names. So let's go through these and classify them. Let's see. I'm going to move the image down so I can write. Let's go through these together. So how would we classify this one? Is it aldo or keto? It'd be keto, right? And how many carbons are in the chain? 4. 1, 2, 3, 4. So what would that be? Tetrose, right. And again, these are just the classifications. These are not the names. What would be?
Aldo.
Okay, it is aldo. But how many are in the chain?
5.
1, 2, 3, 4, 5. So what would that be? Aldo, pentose, right? How will we classify C?
6. Keto.
Right, there's the ketone, so that would be keto.
Hexose.
1, 2, 3, 4, 5, 6. Yes, hexose. What's the classification of F?
Aldo.
Yep, that's the aldehyde. Aldo. And then how many in the chain? 1, 2, 3, 4, 5. So that would be aldo, pentose. Good. What about this one? Keto. 1, 2, 3, 4, 5, 6. Yep. And then last one.
Aldo.
Yep, that's an aldehyde.
Right.
Trios, right? Good. Now remember, these are just the classifications, right? It's just the group, just the family. Do we understand how to do this?
Yeah.
All right. All right, we can skip this one. I think we've already spent enough time on that. Now, let's talk about Fischer projections, because this is going to get old, right? Drawing all these carbons every single time, it's going to get old fast. So we use what are called Fischer projections. And so Fischer projections use lines to represent bonds. And a horizontal line is something that's coming out of the page toward you. Vertical line would be things going into the page. And you need to put the most oxidized carbon, so in other words, your aldehyde or your ketone, that needs to be at the top. So you need to orient it so that either your aldehyde or your ketone's at the top. If you look back at all these, right, the most oxidized carbon is always at the top. Right, so don't draw it with the ketone down here at the bottom or the aldehyde down here at the bottom. Right, always draw it so that it's at the top. And that's just a convention. So a Fischer projection is really convenient for us because it's like skeleton notation, right? You're not going to waste your time drawing all those carbons and hydrogens. Make sense? Okay, so the aldehyde or the ketone is always at the top. So here, there's the aldehyde, right? How did I know that that's an aldehyde? Remember the difference between an aldehyde and an alcohol in terms of how you write it? HO is aldehyde. OH is alcohol, right? So that's the aldehyde. These are the alcohols. So take a second and convert each one of these into a Fischer projection. I'll pause the recording and give you a chance to do that. Okay, let's go over these, see what we got. So we're converting these into Fischer projections. So this is it an aldehyde or a ketone? That's an aldehyde, so we're going to write that as CHO, right? And now we draw our line. And then how many cross lines do we need? 1, 2, 3, right. So 1, 2, 3. So I actually made my line a little bit too long. All right, now we just translate everything over, right? We've got an OH on this side, and an H here, and then H over here, and then OH over here. So we're not changing the orientation, right? We're just taking this Lewis structure and drawing it again as a Fischer projection. And then this CH2OH, we just rewrite it down here at the bottom. Most oxidized carbon is at the top, so we're good to go. Make sense? If we were going to classify this, what would we classify it as?
It's an alpha.
It would be an aldo.
Oh.
1, 2, 3, 4, 5. So aldo pentose is the family, right? Right, that's just the family. All right, let's redraw this one in Fischer projection. So we have our most oxidized carbons at the top, right? But there's still this on top of it, so we still have to draw it. Now we draw our line. How many cross lines do we need? Well, this is a ketone, right? So we're just going to write it like that. And then now we just need 1, 2, 3 cross lines. 1, 2, 3 cross lines, and then put our bottom. Okay, and then everything that's here just goes directly over here. H, OH, OH, and then everything that's over here, OH, H, and H. Right? Every carbon is going to have a hydrogen on one side and an OH on the other side, typically. What family would this belong to?
Keto.
1, 2, 3, 4, 5, 6. Yep, ketohexose. And again, that's just the family, right? That's not its name. It's just the family. Do we see how to do this? Always draw it with the most oxidized carbon at the top, right? If I gave this to you rotated, you would need to rotate it back so that you have the most oxidized carbon at the top. All right. So we've talked about enantiomers already, right? Molecules that are mirror images of each other, but they can't be placed directly on top of each other. We use our hands as a nice example. This is an example of a molecule that would be enantiomeric, right? This is a mirror image of this. But can you take this and place it on top of this? If I take this and place it on top, right? The D and the B crash, the B and the D crash, right? So they're not superimposable. Just like my hands are mirror images, right? But I can't take my left and put it on top of my right. We call those molecules enantiomers, yes? And sugars exhibit enantiomeric behavior too. And so we use the prefixes D and L to distinguish between the two enantiomers of sugars. And so how do you know if it's the D enantiomer or if it's the L enantiomer? This is how you do it. You look at the OH that's furthest from the carbonyl, whether it's an aldehyde or a ketone. Right? So you're going to look at the OH at the bottom. If it's on the left, that's the L isomer. And if it's on the right, that's the D isomer. And most of your naturally occurring sugars are D sugars. Obviously, in the lab, you can make whatever you want. But most of your naturally occurring sugars, for instance, glucose, right, is most present in the D enantiomer instead of the L. So you look at the OH furthest from the carbonyl. L stands for OH on the left. D stands for OH on the right. Right? So this is the structure of ribose. Here it is in the L configuration. Here it is in the D configuration. Right? We're looking at the OH. And so again, these two are mirror images of each other, right? But they're not superimposable. The D and the L are mirror images, but they're not superimposable. I can't take this and place it on top of this, can I? Right? They're enantiomers. And so take this, dump it on top of this, not going to happen. right? This is the L, OH on the left. This is the D, OH on the right. Now this is a really short molecule, right? So there's only one OH to look at. But if it were a long chain, you would just look at the one furthest from the carbonyl. So let's do these together. We'll decide, are these D or are they L? What's this one? This one would be D, right? What about this one? That's L. And then what about this one? That would be something you need to watch out for. All right, it's upside down. Most oxidized carbon's at the bottom, right? You need to flip it. So when we flip it, what do we get? It's an L, right? So if I decide to be tricky, right, just make sure you rotate it before you look at that. Most oxidized carbon needs to be at the top. Do we see how to do this? All right, let's do some more just to make sure we're good. A is which isomer, D or L? L. What about B? L. And what about C? D. Good. Feel good about this? Okay. So the D isomer and the L isomer means that they're enantiomers, right? So if I took D 3-ose and sit it next to L 3-ose, they'd be mirror images, but I couldn't place one on top of the other. All right, now this is something you got to memorize. I told you there are 3 that you have to know the specific structures of. So these 3 sugars you must memorize, okay? You need to memorize glucose, you need to memorize fructose, and you need to memorize galactose. These are the 3 that I make you memorize because these are the 3 most common sugars that you're just going to run into out in the real world, etc. Okay, D-glucose and D-fructose, you need even D-galactose. We're ingesting them all the time. So you need to be able to draw their structures for this class. So what I would recommend doing, maybe just make some flashcards, just practice it. Okay, CHO, and then if I asked you to turn it into the L, everything would be the same except what? If I asked you to draw the L isomer, you would just swap those 2. Okay, everything else stays the same. If I asked you to draw L fructose, everything would be the same, you just swap those 2, right? Everything would be the same, you just swap those 2. So those have to be memorized. And if you don't want to sketch them right now, they're in the slides online, yeah. They're also in your textbook. Okay, so memorize glucose, fructose, and galactose. So let's talk about some biological roles. For us, glucose is the most important sugar, right? You'll hear it referred to as dextrose. You'll hear it referred to as blood sugar. We regulate it with glucagon and insulin, right? Insulin makes your cells absorb it. So if your blood sugar is too high, insulin makes your cells take it in. Glucagon is the short-term energy storage for sugar, right? So if you have not enough sugar, glucagon can break down into glucose. And so maybe you've had this before. Every time I have a pregnancy, I get to have this, right? You measure your blood glucose level, because gestational diabetes is something that you can have during pregnancy, which may not be diabetic regularly. Thankfully, I've always passed my test, right? So you chug this drink. It just tastes like flat soda is really what it tastes like. Everybody talks about how nasty it is, but I think it just tastes like flat grape soda or orange soda, right? You just gulp it back in like 2 minutes. You have to just chug it. And then you get to sit there for an hour. Right? And then you do a blood draw, and you see what's your blood level glucose after an hour, right? So you should expect it to go up and then go down, right? If it's not, or if it goes down too low, right? Those are the ranges where you don't want it to be, those are where you want it to be. So obviously you can do this at times other than pregnancy, but that's the one that most comes to mind for me personally. So let's talk about cyclicization. Now the good news is you have seen this before, kind of. So we're going to take our Fischer projection and we're going to turn it into a Haworth structure. Okay, that's how you pronounce that word, Haworth. So we're going to take those Fischer projections and we're going to turn them into Haworth structures. So what happens when you take a sugar, this is not what it looks like in solution, right? If you take glucose and you dissolve it in water, it doesn't look linear. It actually cyclizes around like this. So what happens is this hydroxyl and this aldehyde react, right? And we get a cyclic, okay? And that's what, we've seen the reaction between an aldehyde and an alcohol. We've seen that before. So that's not new, but that's how we make this into a ring, okay? This OH becomes, essentially you could think of as an ether, right? It's cycled the ring back around on itself. So if you have glucose and you dissolve it in water, don't visualize it like this. You need to visualize it like this, because that's really what it looks like when you dissolve glucose. There's going to be a small percent that, you know, is still linear, but the vast majority is going to be in the Haworth, not in the linear. Okay? So let's talk about how we do it. Now again, we're not going to go through this in the great detail that you will get into when you take organic, because this is elementary, right? We're not looking at every gross, disgusting detail in this class. We're just getting the big picture, right? So we've got the OH right here. This is carbon, let's see, 1, 2, 3, 4, 5, 6. So that's the OH on carbon 5. So the OH on carbon 5, okay, and the carbonyl on the aldehyde, right? And notice you get two options. You get an OH down on carbon 1 and an OH up on carbon 1. You're going to get two options. And so we distinguish them between, we call one the alpha and one the beta. If the OH is down on carbon 1, that's the alpha. And if OH is up on carbon 1, that's the beta. Okay, because you're going to get two options. Notice everything else is the same. All right, so we're going to do a glucose. We're going to do a fructose, because, right, glucose is an aldose, fructose is a ketose. We're going to do them together. So what I actually recommend doing, I'm going to go through it with you. I think it helps to see it worked out on paper. So let's just do something here. Oops. New slide. Just want it to be blank. Now this is a figure from your book. So I'm going to crop it real quick, because I want you to see me work it out. I think that's going to help you more than me just kind of lecturing to you. I need to make this smaller so I can write, since I'm not 8 feet tall. All right. All right, so what we do, we take our Fischer projection, okay? Now after you do this enough times, you can do it in your head. You won't need to redraw it. But as you're getting started, I really recommend that you redraw it, okay? Because it's hard to visualize. So let's first draw this as a Fischer, right? Because I don't want to deal with all these Lewis structures. So we've got CHO, and then 1, 2, 3, 4. 1, 2, 3, 4. And then there's my CH2OH. Okay, so then we've got OH, H, OH, OH, which means on this side we've got H, OH, H, H. Okay, so what we're going to do, let me get rid of that now. Delete. What we're going to do is we're going to number our carbons, okay? 1, 2, 3, 4, 5, 6. Don't forget this one down here at the bottom, okay? Now again, after you've done this enough times, you probably won't need to actually draw it, but I recommend doing it at the beginning. Rotate it 90 degrees, okay? So redraw it written out this way. There's that stupid seam always in my way. All right, so we've got CHO, right? And then we've got 1, 2, 3, 4 cross lines. 1, 2, 3, 4. Maybe I can just, acid altogether. Okay, so there's carbon 1, 2, 3, 4, 5, and then there's 6. Now, you're just going to rotate everything, okay? Everything that was on the left now gets drawn on the top, right? So this is H, this is OH, this is H, and H. And then everything that's on the right is now on the bottom, right? So OH, then H, then OH, and OH. So again, after you've done this a few thousand times, right, you'll probably not have to do this step anymore. You can just visualize it. But what's going to happen is here's your aldehyde, and the alcohol on this run, carbon number 5, are going to make a ring. So this reaction is going to occur here. Now this is a 6-membered chain, so you're going to get a 6-membered ring. All right, 1, 2, 3, 4, 5. Because notice it's the O in the OH is going to be in a bond with this carbon, carbon 1. See? 5, O, there's the O right there. And then there's the bond with number 1. And so now we're going to draw sticks. What happened to carbon number 6? It's still right here. So there's carbon 6. It doesn't go away. All right, now here's the nice part. Because you've already rotated this 90 degrees, you can just directly translate it down. Okay, now problem is with carbon number 1. Because carbon number 1 is going to get an H and it's going to get an OH. How do I know what to put on carbon number 1? Remember, if it's alpha, that means C1OH is down. And if it's beta, that's a 1. C1OH is up. So I'd have to tell you, draw it in the alpha configuration, draw it in the beta configuration. And if I don't specify, then you can draw either one. Okay? Let's just pretend that I told you to draw it in the beta. Let's just pretend that that's what I told you to do. All right, so if I said draw it in the beta configuration, that means that carbon number 1 has OH down and H up. So the way you figure out what's going on carbon number 1 is you look at the problem. Is the problem asking for it to be alpha or beta? And if the problem doesn't specify, then either one's fine. Okay? But now look at 2. H up, OH down. So we draw H up, OH down. Carbon number 3, that's an H. OH up, H down. OH up, H down. Carbon number 4, H up, OH down. Now carbon number 5, remember it's got the O that is now right here. And it's got a bond to the CH2OH. And what else does it have? You have to put one more thing right here. There's a hydrogen. That's all that's left. Okay, so there's nothing special. Markers get low. And so this would be beta D-glucose. Right? This is D-glucose. And this would be beta D-glucose. Right? This is the Fischer projection. This is the Haworth projection. Does this make sense? Currently, my #1 video online is on this, which kind of makes me laugh, because apparently that's like one of the popular topics on the webpage, which is kind of cool. I wasn't intending for a 4-minute video that I made to be the most popular one, but that's the most popular one right now. Okay, so we see how to do this? All right. So if we want to use the figures from our book, this is just using figures from our book. Oops. Right, so this is using the figures from our book. We rotate it, and then we cycle it around, we get our generic product. Again, alpha has OH down, beta has OH up. So those are the figures from your textbook. But I really think it helps more to see someone walk through it than just me show you the slides. So if I don't specify whether you draw alpha or beta, then you can draw either one. But just make sure you know the difference between the alpha and the beta. Make sense? All right, alpha and beta again. So let's do this one. I'm going to pause it for a second. I want you to try turning this turning this Fischer into a Haworth. I'll pause it, and I'm asking for it to be in the alpha configuration. All right, let's go over this one. Move this way over here and shrink it down. Because Lewis structures are a pain, right? They're a pain. They all know it. So let's first convert our Lewis structure into a Fischer projection. Then we'll convert our Fischer into a Haworth. So first things first, we draw it in a Fischer. So CHO, and then 1, 2, 3, 4, 1, 2, 3, 4, and then CH2OH. All right, and then we've got OH, HH, OH. So on the opposite side, that would mean H, OH, OH, and then H. All right, now we're going to go through and number 1, 2, 3, 4, 5, 6. So the first thing I want to do is I want to rotate it 90 degrees. Again, after you've done this enough times, you can probably just visualize it, but until you get to that point, redrawing it will really, really help. Okay, so anything that's on the left is now up. So H, OH, OH, H. Anything that's on the right is now down. OH, H, H, OH, and then don't forget our numbering, right? This is carbon 1, 2, 3, 4, 5, and 6. So where is our product coming from? It's going to be the reaction between this and this, right? So this is going to give us a 6-membered ring because we're going to have 1, 2, 3, 4, 5, 6, right? If you want to think of it in terms of how many members are in our ring. So 1, 2, 3, 4, 5, and now let's give our sticks. What happened to carbon number 6? It's just hanging out as CH2OH, right? Nothing happened to it. It stayed the same. Now the problem asked for me to draw this in the alpha configuration. Problem said draw it for me in alpha. So on carbon number 1, do I have OH up or OH down? Down. OH down, right. And H up, right? Because the problem said give it to me in the alpha config. So that's why we did it this way, right? And now everything else just directly translates. So 2 has H up, OH down. So H up, OH down. 3 has OH up and H down. 4 has OH up and H down. And then don't forget what else is on carbon number 5. It's got the CH2OH, it's got the bond, it's got this bond, it needs a hydrogen here as well. And so this would be alpha D-galactose. See how to do it? Feeling good? Any questions? All right.
If you get the Haworth, how do you know it's D? Or like, will you always start with that one then?
Well, if I tell you to go backwards from Haworth, I would have to tell you to draw it in D or draw it in L. Yeah. So next week we're going to do some enrichment on this, and if I give you the Haworth, which I will, I'm going to be giving you Haworth and saying turn it back into Fischer, and I would have to tell you if I want it in the D or in the L. Yeah. So we can skip over that. All right. Let's look at fructose. So I'll give you a second to jot this down. But like I said, I think it's more beneficial for you to see it walked through than for me to show you the generic textbook slides. So I'll give you a second to jot that down. I'll even pause the video so there's not dead air. All right, let's go through this one. So again, that's the Lewis structure. Lewis structures are annoying. So let's stick this off to the side. Let's convert our Lewis structure into a Fischer projection, which will then turn into a Haworth. And just for fun, do you want to draw it in the alpha or the beta? All right, let's draw alpha D fructose. All right, that's the directions. So first we're going to take our Lewis structure, draw it into a Fischer. So we've got CH2OH, and then we've got our ketone, right? This is a ketose. Then we've got OH on the left and H on the right. We've got OH on the right and H on the left. We've got OH on the right and H on the left. And then we've got our CH2OH. The reason I've got this little arrow here, the reaction in the aldose is between the aldehyde and this OH, right? It's between the aldehyde at the top and this OH in the aldehyde version. But there isn't an aldehyde here anymore, is there? So it's now the reaction between this and this, right? It's going to make our final product look a little bit different. But before we start worrying about what our final product looks like, what do we do first? We're going to number, and then we're going to what? Turn it 90 degrees clockwise, right? So we've got CH2OH, and now we've got, anything on the left is now on top, HOH, that's number 6. This is number 5. On 4, we've got H up, OH down. On 3, we've got OH up and H down. Carbon number 2 is our ketone, which you can draw whichever way you want. That doesn't matter. And then you've got CH2OH. Right, there's carbon number 1. So the reaction is occurring between this O and this carbonyl, right? So our product is actually going to have 2 CH2OHs now, right? It's not going to have just one CH2OH like in the aldehyde analog. It's going to have 2 CH2OHs. So our product, this is going to be, this O is at the top, and we're going to have a 5-membered ring. All right? It's a little different. So we've got CH2OH. Now I said draw it in the alpha. All right, so we've got our CH2OH down, right, and H up. So there's carbon 1, there's carbon 2. Now look at carbon 3, OH up, H down. There's carbon 4, H up, OH down. So there's carbon 3, there's carbon 4, here's carbon 5. Carbon 5, it just has the CH2OH. And then another hydrogen, don't forget that, second hydrogen. Made my O here disproportionately large. There we go. It's a little bit more to scale. Do we see how we did it with a ketose? Our final answer looks slightly different than with an aldose. Does this make sense?
Yeah. So on these, you can't number from either way you want to, right?
What do you mean you can't number any way you want to?
Like to do the alpha and beta, you always have to go clockwise, right?
Well, you're still going clockwise.
Like you can't.
But alpha has the CH2OH down. And if I said beta, it would be on top.
So, but to do, you have to go this way for it to get the right answer, right?
Mm-hmm. Yeah, yeah. I think I've got one more of my slides here for you to do just for practice. Let's see. I just say practice problems, but then I don't have actual practice problem in there. So I'll just give you, I'll just draw a blank one. Oh, hush. I'll just draw a generic one on the board. How about that? All right. So why don't you take a second and do this one? I'm just going to make something up. All right, so you give me the beta configuration. And I will pause the recording and let you try that. All right, so here will be our practice problem. All right, so the first thing we're going to do is we're going to rotate it. Well, we're going to number. All right, 1, 2, 3, 4, 5, 6. We're going to rotate so we get CH2OH. And then we've got number 6. There's 5, OH up, H down. There's 4, H up, OH down. There's 3, OH up, H down. There's 2, that's our carbonyl, and then here's 1. Okay, so we're going to get the reaction between here and here. Right, so give myself a little more space to write this time. So here and here, that's the bond between that OH and carbon number 2, right? So there's carbon number 2, 3, 4, and 5, right? So now we draw our sticks. All right. We want the beta, so that means we want OH up, CH2OH. There's carbon number 1. All right, 3, just directly translating, OH and H. 4, H and OH. And then 5 has got our CH2OH. And then we can't forget that lonely hydrogen. Feeling good? All right. Well, on Monday, we're going to do enrichment on this. That's what we're going to spend the whole time doing. So come prepared for that. And then there's just the figure with the alpha and the beta in the ketone analog. Leave you with that. All right, so on Monday we'll be doing enrichment on this, where I will give you the Haworth and you convert it back to Fischer, or I give you Fischer and you turn it into Haworth. Right, that's what we're going to be doing on Monday. And then we'll also be moving on to disaccharides next week as well. So that's where we will stop.